and he's an expert in organometallic synthesis. He's going to talk to us about synthesizing nanomaterials.
Thanks, Yao. Okay, so as Yao said, I'm going to be discussing nanomaterial synthesis in a very broad swath today, with a specific focus on how nanomaterials are impacting PV and PEC water splitting. Although before I start, I need to alert you guys that I do have 2 eye clickers, so be prepared. And secondly, I need to correct Art Nozick. I am not the expert at NREL in the 2.6 and 4.6 nanomaterials. There are a couple in the audience, Julie Luther and Barbara Hughes, who's a grad student here at CU. I see lurking. I'm working on some group 4 and 3.5s, and if you want to hear about the quantum dots that we're making in those fields, my talk is Friday on that section. So, unique properties of nanomaterials. As Art just told us, they have very tunable optical absorptions. They can participate in multiple exciton generation. They have some relaxed materials requirements, which I'll get to, and I'll detail all these a little bit in a bit. And they can orthogonalize light harvesting and transport, which is very important for things that have relatively poor minority hole conductivities. And they also can have high surface areas, which can have some very unique impacts on some of the PV and photoelectrochemical water splitting fields. And so first, tunable optical absorptions. These can really have, we can really have a dramatic variation in semiconductor particle properties based on their band gaps, particularly. We can show they have large blue shifts in the absorption edge. We go from a situation in semiconductors where we have bands, and so the energy levels are all pushed together, whereas in nanoparticles in particular, and all other nanomaterials, the energy levels become discrete, more like molecular systems. Finally, it's been shown that you can also convert indirect semiconductors into direct semiconductors, and vice versa. So MEG, I'll just briefly skip over this slide since we had one of the world's foremost experts in the topic give us a talk there, but that's one thing. Secondly, you'll see here, this is actually the same image that I stole from one of Art's talks that you can find online. This is the quantum dot image, and I'll just say that for a 5 nanometer quantum dot, it has roughly about 5,000 atoms. And if you think of that relative to bulk photovoltaics, for instance, you can see here that if we have 100 ppm impurities, that's about 10 to the 20. So that's because everyone knows how many atoms in a mole. This isn't the clicker, right? About 10 to the 24. So we're talking about 1 atom defect in a quantum dot, which is virtually a perfect quantum dot, having already 100 ppm impurities relative to bulk films where they're purposely putting in, say, 1 ppm of dopants. And so the nanomaterials are significantly different from their bulk counterparts, and these things really work well despite having significant impurities. The other thing I'll note is that nanomaterials can be made rigid or flexible, whereas typical bulk semiconductors, organics excluded, you're not dealing with the flexible properties. Okay, and so here's something that you're going to want to study a little bit for your iClicker quiz. Orthogonalized light harvesting and transport. So in typical semiconductors, and I apologize, this appears fairly dark from where I'm standing, but you'll have a PN junction film with the junction at the green-blue interface here. The light comes in and generates a electron-hole pair, and then the minority carrier needs to diffuse with this diffusion length L here all the way to the junction, and then the majority carrier goes down and is collected at a back contact. And so if you have a situation where a semiconductor has a very poor or low minority carrier diffusion length, short minority carrier diffusion length, you can end up with recombination occurring and your efficiency is really poor. Nanomaterials can solve this problem because you're light harvesting, so if your photons are coming down coincident with the axis of, say, this nanorod or nanowire array, the minority carrier only needs to diffuse as far as that junction. And so this diffusion length L can be significantly smaller, which results in, as shown here, a much higher efficiency for quantum yield in the red part of the spectrum. And so I'd like you all to think a little bit here about why this is. I just told you the main reason, and that's the minority diffusion carrier length needs to be significantly less. But there are other reasons why that might be. The first one would be planar samples can't necessarily collect as many red photons as, say, the nanomaterial. That's one option. Second might be that the planar sample, simply because it is planar, reflects too much light. The nanorods might promote something called light scattering. Could be both of those. Or, I may be giving you a trick question, the non-normalized planar sample might actually be better than the nanomaterial. So why don't you all talk to your neighbor for 30 seconds or so. Let me know what you think, and we'll come back here. Final votes here before we talk about what that is and why. Okay, so for me, I'm actually a little bit disappointed that nobody voted E, because E is not the right answer, but it's partially right. So, in fact, there's a couple things I want to point out here. It is partially a trick question. The non-normalized planar sample is much better. If you look at the JV curve, or JE curve, as Nate Lewis has plotted it here, this is the JV curve of the planar sample in the light. And that's versus the red curve, which is the nanorod sample in the light. So it is a much better material for photoelectrochemical, whatever reaction they're doing here, probably hydrogen production, than the nanomaterial. And so that brings up the point that how you plot the data matters, right? I can plot the data like this and say my material is the best in the world, but if I plot the data like that, well, okay, it's not the best in the world. So that's one point. But I'm happy to say that most of you got it right. The vast majority here, about 2/3. It is D, which is both B and C. So planar samples in photovoltaics, they often have anti-reflective coatings on them because reflection of light is a huge issue. It can be up to 20% of the light that hits the cell can go down and just be reflected away before it even hits your active material. Nanorods and nanowire arrays have also been shown in the scientific literature over the last 5 or 10 years to promote significant light scattering. One, they mitigate this reflection, and two, they promote light scattering so that light sort of bounces around within the active material because it's going, if you look at this type of array here, it's crossing from typically a high to a low dielectric constant material, high dielectric being a semiconductor, the low dielectric to the interstitial space between them, filled with, say, an electrolyte like water. And that will cause lots of light refraction in that material, which will lead to this high scattering. And so it is B and C. Congratulations to those of you who didn't, but I think it was really instructive to look at how data is presented as well. Okay, so the last point about nanomaterials in general and why I'm in this field and why others like it. And this image here was actually created by Yao. I'll give credit where credit's due long ago. They have high surface areas, and so you can make things like dye-sensitized solar cells, which wouldn't otherwise be possible without the high surface areas of nanomaterials. I'm sure other people have already spoken about dye cells, and other people will, so I won't go into the details there. Similarly, with photoelectrochemical cells, it's a system where if you have a high surface area, you can reduce the exchange current density, which is effectively the charges that are doing the redox reactions at the anode or the cathode, that is taking water, producing oxygen, or producing hydrogen. Those charges have to react, and the faster they have to react, you have a greater exchange current density, and that puts lots of limitations on your catalyst at the surface. And so if you have a lower exchange current density, then your catalyst doesn't have to work quite as fast, and so that makes it a lot easier catalyst to design. Okay, so as I said, I'll be talking about quantum dots on Friday morning, and today we'll be discussing metal oxides for dye cells and photoelectrochemical cells, as well as inorganic sensitizers for dye cells. Let's see how I'm doing on time here. Good. Okay, so this image isn't reproducing particularly well, but this is ilmenite crude ore. This is your iron titanate, and that is the raw material for titanium dioxide. The reason I start with titanium dioxide, this is the material that is mostly used for dye-sensitized solar cells for the photoelectrode, and it's also the one back in 1972 that made the revolution for photoelectrochemical water splitting in metal oxides. And so there's two processes to make this. One's called the Fluoride Process. It's really ugly, where you use 6 equivalents of carbon as a reductant, chlorine at very high temperatures. You get out these metal chlorides, and you can distill out your tickle, and then you oxidize it in a plasma flame and get out your TiO2. If any of you have made dye cells, you might have heard the name Degussa P25. It's not particularly good, but it's the commercial standard, and this is these two methods are the methods by which you make TiO2, which is a massively produced industrial chemical. It's the white pigment in paint, for instance, and so we're producing tons and tons of this every year. There's another process called the sulfate process, which is very similar, except you digest your ilmenite crude ore in concentrated sulfuric acid, another very standard reaction that all of us chemists love to do. Make your titanium sulfate, and then here you can actually crystallize out your iron, and then you oxidize your titanium sulfide to make your TiO2. So there's slight differences to this process, so these processes won't get into the details of why one makes a mix of anatile and rutile, and the other just anatase. But suffice to say that Degussa P25 is pretty bad when you make a dye cell out of it. You can crank out something around 5%, but when the world record is 10-12%, you're wondering what you've done wrong. And so the alternative to that is to use a solvable thermal route. And this is a route where you're using typically a metal oxide precursor. You're doing this in solution and at temperature, so hence the solvo and thermal. And you can make either anatase or rutile, depending on what your starting conditions and your pH are. You're starting a titanium precursor and your pH are, and you can have excellent particle size and surface area control, and these result in particles with the best surface area. And so, as a postdoc at NREL in the early to mid-2000s, I did some research on solvable thermal method for TiO2. One of the big frustrations that I had was nobody wrote down a reproducible method to get particle size X. And so I basically went through the process and looked at two different routes. One, you took the titanium precursor, and that was an acetic acid. The other was more of a nitric acid-based prep. And here are the conditions here. You can read it in the paper. And basically found that if you control all the conditions perfectly, and you don't deviate from this, and everything's the same except for your temperature, so this is your autoclave temperature, you have a sol, which is basically an incompletely condensed titania precursor, and then you heat it up in an autoclave, which is simply something that seals up, and you can heat water to 200-300 degrees. You end up with a nice linear correlation between your particle size and your autoclave temperature. And so that gave us, along with a number of other studies, some confidence that we had particles that were reproducible and simply varied in size and not other properties. And so that allowed us to do a lot of other studies that I'm not going to talk to you about today. But another route that we started working on, and this was sort of spurred by some work that Craig Grimes had done when he was still a valuable professor at Penn State, which is no longer the case. If you follow the scientific literature, you'll know why. I won't comment why, but oriented TiO2 nanotube arrays is another type of nanomaterial that has been widely used now for dye-sensitized solar cells. And we were able to show that at the same thickness, so these are microns of thickness of your film, so measuring from the electrode to the tip of the conducting electrode to the tip of your nanomaterial or your nanotube, that the nanotubes were actually relatively superior to their nanoparticle cousins, and that had to do with the fact that these had better light harvesting and charge collection efficiencies. And so this is a synthetic talk, so I want to focus on that aspect of this work. Making these is a relatively simple thing. You just take a fluoride-containing electrolyte, and you have a two-electrode system where you have a working electrode and a counter electrode. And the chemical reactions are shown here. Basically what happens, in this case I'm showing it on a transparent conducting oxide substrate. What happens is you have dissolution of your titanium hexafluoride anion, which is produced there under these bias conditions, and then you have further reaction of titanium metal that's then exposed by that dissolution to make your titanium. And the titania, I show as TiOX. You do need to anneal it to get crystalline anatase. If you anneal it too long, you get rutile. In this case, this is the first time we're able to reproduce this on a transparent conducting substrate, which, as noted before, we just did it on titanium foil. And so you can either do this, it's the exact same reaction, except there's this interfacial layer called niobium-doped titanium oxide that we put on the surface as a protecting layer. And you're able to get either transparent or opaque titanium nanotubes, titania nanotubes. And so one of the other things we discovered along the way is that if you take these nanotubes after you've produced them and you let them air dry, the capillary action of the water drying actually brings the tubes together. And so here you can see on the left is what happens to an air dried film. It's a 1 micron, they're relatively, we're looking top down, scanning electron microscopy image here. The 1.1 micron sample looks pretty good, and then as you go to 3 micron or 6 micron, they really bundle up together. And then we discovered that if you dry these in supercritical CO2, you can retain their nice oriented rather than bundled architecture. And so that was a really nice result. Switching gears again to another type of electrode that one might use, you can use nano wires. These are nice vertically aligned nano wires. There are a number of reports on things that look like this. The substrate is shown down here, and then the nano wires grow off the surface. You do this in one of these autoclaves again, and in this case they're nice Teflon lined things, and you can orient your sample at an angle, and then the nano wires will grow off the bottom of your sample. You need to make sure you put your conducting side on the bottom, or else you'll be growing in the wrong way. And so there's various things, recipes that you can use to do this. I just highlight a recent one here, and you can see that they're comparable to their nanoparticle cousins. In this case, the key result here was that this was the first time that anyone had shown that, as one would expect intuitively, if one has a single crystal wire that where the axis is oriented along the c-axis, the 001 growth direction, that you have transport that's faster than in the nanoparticle systems. In the nanotube systems, that's actually not the case. And so that was a surprising result for us. And so to show that that's actually, you have a one-dimensional channel or pathway for your electrons to transport through, that does result in faster charge collection. And so to sum up this section, I'll say that there's lots of other methods that one can use. One can use anodized aluminum oxide templates. This is a sample that I made many years ago. It's very similar to the TiO2 nanotube method. It's just anodization of aluminum metal, and you effectively are able to drill these beautiful oriented aligned channels down, and then you can deposit things within those channels, dissolve away your template here, your AAO or anodized aluminum oxide membrane, and result in something that looks like this. This didn't reproduce very well, but this is a three-dimensional picture of a ordered porous film. So here's a review on how one might do that using various surfactants. This is a head-to-tail surfactant that I've shown. The P dots are supposed to represent growing soil. And so they organize them around these micellular type structures. And depending on what you do, you can get either 2D or 3D, cubic, hexagonal, all sorts of different types of gyroidal structures as well. And so over here I'll also show the inverse opals. So these are ordered, in this case polystyrene. You can use silica or other different types of beads as well. And then in this case I electrodeposited cadmium selenide around the outside of those beads, and then you dissolve the beads away, and so you're left with the relief of that structure. And so there's lots of different ways this can easily be done, and has been done with TiO2 as well. There's lots of different ways to make nanomaterials for dye-sensitized solar cells, and hopefully I've captured that a little bit for you. So Art's finish to his talk was actually a great lead into where we're going next. And so I'll change gears a little bit to photoelectrochemical water splitting, which from here on out I'll probably just say PEC. So Art mentioned that he thinks the Z-scheme, which is a two-step system, is definitely the best and the way to go, and I'm in agreement with that. And so I'll get to that in a second, but there's a lot of other people out there who are popularizing the magic pixie dust approach. So basically you make all these metal oxide nanoparticles and you sprinkle them into a beaker of water and you shine light on it, and out frost lots of hydrogen and oxygen. And so that actually can happen, but there are a lot of technological issues with that. Basically what's happening is you're producing oxygen via this reaction here, as well as doing the hydrogen reduction from H+ ions that are generated from this reaction at a different part of the particle, and presumably a different catalyst. And so there are some benefits to this approach. It's certainly simpler to just sprinkle some particles into a vat of water and off you go, but it's also much more challenging, as Art's graph showed. The theoretical efficiency that one can get from something like this, which is just a single absorber, is far, far lower than you can from a tandem absorber structure, a two-step Z-scheme system. And so here in the orange bar is the first absorber, and so typically this is a higher band gap material, and so you'll be absorbing your blue light. The red light will pass through a conducting transparent substrate, and the red light will be absorbed by a second semiconductor. And so this is one way that we hope to achieve to direct water splitting hydrogen production on the order of 15% efficiency, although theoretically you can get higher than that. But technologically that would be a great breakthrough if we could do that. And so metal oxides, as I noted before, since the early 70s have been promoted as one of the best materials for these types of photoelectrochemical systems. The problem with those and many other semiconductors is they potentially have a large band gap, they have slow charge carrier dynamics, poor interfacial kinetics, so that's how the reactions happen at the surface to actually make the hydrogen and oxygen from water. And it's not as much of a problem for metal oxides, but certainly for other semiconductors that have been tried, more the photovoltaic, traditional photovoltaic type semiconductors that you can think of, photocorrosion is a big issue. Because you're doing chemistry in water with lots of photogenerated charges, the fact that you have a metal oxide already means that you're probably not going to degrade the material. And so it's my opinion that metal oxides are the way to go. As far as Art was suggesting, you really need to bury the junction and get that junction away from the redox reactions at the surface. And so if one wants to have reactions right at the surface, though, metal oxides are the way to go. Here are the three basic reactions, and I'll point you to 3 excellent reviews on the topic if you you want to start delving into this literature a little more deeply. And so this is a gunshot approach to some of the best materials that have been shown to date. I already noted TiO2 from Fukushima and Honda back in '72. There have been various attempts over the last 4 decades now to either dope or alloy these metal oxides. Doping them basically makes a doping layer, and so this can effectively reduce your band gap, and similarly creating an actual new valence band that's above where the oxygen 2p dominated valence band would be is another strategy. And so most of these materials here deal with one or the other of those types of strategies. And so I'm going to just now spend do you have a question? Go ahead.
Can we go to the slide here? So are only the people trying to increase the position of the valency band maximum? So are there any trials to bring the conduction band maximum minimum down?
So this next slide might address that a little bit. There's when you're dealing with PEC water splitting, and I didn't want to go into this in detail, but the position of your valence band is critical. It has to be below that of the water oxidation potential, and then there has to be this difference in what are called the overpotential for your catalyst to actually do that work. So typical catalysts will require 300, 400, 500 millivolts of overpotential, and those are some of the best catalysts known. On the hydrogen side, your conduction band needs to be above that of the hydrogen production potential. And so there are energy constraints that basically will pin the conduction band to a certain level. Pushing it down significantly oftentimes will put it below the level of the hydrogen reduction. And so most of what people are doing is trying to move the valence band up, because oxygen, if you look at an energy scale, energy's up. The oxidation, water oxidation potential can be right around here. And so there's a huge difference to go from oxide-based metal oxides. So you typically have a huge overpotential, which just represents loss. So that's why most people try to push it up. And one way to do that is to blend with less electronegative elements like nitrogen. Nitrogen, this is just a valence band structure here, can push that valence band level up, and that's been shown for this yttria, titania, oxynitride, tantalum oxynitride here. And so you can see here, this is the yttria tantalate here, and so when you add nitrogen in there, you significantly redshift the absorption. And so synthetically, how one does that, this is very typical of how, I would say, many material scientists approach the project. Just throw two things together and heat it. And that's basically what they do here. And then they heat it some more with ammonia gas. And so industry doesn't particularly like these methods because heating to 850 C requires an intensive amount of energy. And so you're putting so much energy into the system that are you really going to get that payback? And the same holds true for traditional PV materials. The other thing that I don't like about this is you get a non-stoichiometric yield or product. So your yttria to tantalum is not 2 to 2. You also have a very low surface area. I showed earlier what the benefits of a high surface area are, particularly for PEC water splitting. Even though they're selling this as a nanomaterial with 20 to 100 nanometer diameter particles or crystallite grains, you actually have 0.5 micron to 4 micron aggregates, and that results in this low surface area here. The aggregates come from basically particles sintering together at these high temperatures. And so there have been a lot of people who have been out there working on other ways to make these, and one is a physical deposition method. And so they're in a tube furnace, which is shown here. You can orient your sample either vertically and have the gas flow from left to right, or you can orient it horizontally, as I've shown here, with the gas again flowing from left to right. There's a manufacturing process that's actually used for PV where they have the gas streaming down, and this is sort of a conveyor belt, and the actual substrates are moving from left to right. But suffice to say that it's much the same as this method here. So they're calling this atmospheric pressure chemical vapor deposition. And basically, you take an iron precursor, TIOS, which is tetraethyl orthosilicate or tetraethoxy silane. There's a bunch of different acronyms for the same thing, but it's basically a SiO2 precursor and some dry air, and you end up with a silicon-doped iron oxide. And so this was performed within the last several years by Michael Gretzel, who was the originator of the dye cell, and he was actually, and still is, a great photoelectrochemical scientist, and started in the field of PEC water splitting, and then said, oh, well, what happens if we throw a dye on it? Well, now we have dye cells. So he's now going a little bit back towards PEC water splitting as well. But in any case, you can see some of the conditions here. So this is a nice method that's been developed and has been known and used in the PP industry for quite a long time. Combinatorial routes, you've probably heard about combi. You can do this by electro deposition. You can ultrasonic spray or sputter coat metal ions, but in all cases you pretty much have to calcine these. And so basically what you do here is you'll have a grid, say, in one corner you'll have an iron, in another corner aluminum, and another corner here 100% cobalt, and you have various gradients over this particular triangle. And then you do a little photoelectrochemistry, and you see where you get a hot spot, and then you actually probe that hot spot a little bit. And this is a instant photon current efficiency, or IPCE, external quantum yield of this cobalt iron aluminum oxide, which has a band gap about 1.6 eV, which, as Art was saying, is just about perfect. So that's one method. You can also do electrochemical combis. So there's like 128 well plate here. So there's a lot of different methods that you can use. At NREL, we have a huge computing group, which is also doing combinatorial, not synthesis, but at least prediction via their computing techniques, and are finding a lot of new materials and new phases that should exist thermodynamically but haven't been discovered yet. So that's another approach. And then people like myself and Bruce Parkinson and others then try to make what they predict. And so metal oxides can also be deposited electrochemically here. Jason Siebold, one of our audience members, is actually the one who developed this, and that was published this winter in JAX. So this is a bismuth vanadate sample here, and in this case we have a 3-electrode system, and he makes a initial bismuth vanadate precursor here, and then heats it at high temperature, which gives excess vanadium. As you can see here, the bismuth and vanadium are not one-to-one as they are in the product, and it dissolves out that excess vanadium to make the product. You can see that it might be both, but there's certainly some nanostructuring going on here. And when you interface this with a iron oxo-hydroxy catalyst, you can see that he made quite a bit of hydrogen. The dashed curve here is 100% Faraday efficiency, so that's what one would expect if you were to get perfect energy in, energy out. And so as you can see, they're very close to that, at least for the oxygen side. They would have to add a little bit of potential in order to also produce hydrogen at the same time. And so there are some alternatives than simply heating everything to 500 or 800 degrees C, and some of which I'm interested in. And an interesting alternative here was to actually just dope it with hydrogen. So taking titanium dioxide, which people have been working, as I showed you, for the last 40 years on making better. Just last year, there was a science paper that came out by two LBNL, Lawrence Berkeley National Lab scientists, where they took TiO2 nanoparticles, which are typically white dipped in paint, right? And they heated it to moderate temperatures, but at 20 atmospheres of hydrogen. So not exactly what I would call mild conditions either, but they did achieve this sort of black powder at the end. They claimed the band gap went down significantly, and then they showed that it does produce hydrogen. So in this case, they pushed the valence band up too far to produce oxygen, and so they're only getting hydrogen out. But this is another really interesting step in a good direction forward for the metal oxide PEC water splitting field. So I'd be remiss if I didn't mention the alternatives to metal oxides really briefly. John Turner at NREL still has the world record efficiency for unbiased solar to water, solar to hydrogen water splitting. And basically that's a modification of a photovoltaic cell where you have a photoelectrochemical P-type gallium indium phosphide where the hydrogen production happens, and on the backside you have this buried junction, as Art was saying, the buried junction here protects a PN gallium arsenide photovoltaic cell, and you're able to then produce oxygen at this platinum counter electrode here. So it's pretty amazing. You can literally just take this film and drop it in water, shine light on it, and bubbles will start growing off of both sides, hydrogen on one side, oxygen on the other. The problem with this is that particularly this P-type photoelectrochemical side does photocorrode, and so again, this is sort of the death knell of your more traditional photovoltaic materials that are used in PEC water splitting. You can see it's not an oxide, and at the end, when you're done, there was a little O-ring around here. You're left with a huge pit where your material has dissolved effectively and made probably gallium indium oxides here. And so John's actually been working a lot on preventing this photocorrosion, and he's had some success there. And so there's various surface treatments and things that one can do to try and fix that. But again, if you start out with metal oxide and you end up with metal oxide after photocorrosion, you're okay. So lastly, I just want to quickly, in my last 5 minutes here, move to inorganic sensitizers for sensitized solar cells. In yellow here is the solar spectrum. Anybody familiar with dye-sensitized solar cells? We have two main dyes. One is the N719, which is a ruthenium. Oh, look at that. Microsoft Word quit unexpectedly. PowerPoint. Let's see. One thing we can do is call it, and I'll just finish tomorrow on Friday. Doesn't appear to be coming back up there. The program's open, but it's not opening any files at the moment. Oh. Oh, there we go. Let's see if I can launch it. Huh. There we go. I'll try and fly through this. So basically there's lots of different ways you can think about to make dye cells better, and one of them is to create new sensitizers that absorb more of the solar spectrum. And there's a lot of different ways one can do that. There's these ETA, or extremely thin absorber cells, there's quantum dot sensitized solar cells, and there's also these relatively new two-phased sensitized solar cells where the sensitizer is also the charge conducting phase. And so we were very interested in that and ended up electrode depositing copper indium diselenide within the pore space of the nanotube array that we synthesized. So here you can see is the empty array. Doesn't reproduce particularly well, but this is the partially filled sample, and then after you over deposit. And so There's been a lot of work in this area, but in general, most of these things don't work particularly well, including ours. And the reason for that is because you have these highly defective surfaces. So you have huge amounts of interfaces between your two nanomaterial phases, and the result is significant amounts of defects. And so atomic layer deposition is one way that one can use to try and prevent this, or to make better quality nanomaterials. I really like this method. If you're not familiar with it, I point you to a review by Steve George, who's in the chemistry and biochemical department here at CU Boulder. And we worked with Steve to develop a procedure where we made indium sulfide, which is a semiconductor. And I won't go into the details here, but suffice to say that we did make it. These are some of the surface reactions that happened. And so we showed via X-ray reflectivity and QCM, which is quartz crystal microbalance, that we do in fact make what we think we make. And finally, we also have this XRD spectrum, which took 2,000 cycles. So basically, you're pulsing the gas of one precursor, pulsing another. So in one case, the indium precursor, the other the sulfide, and you're ending up with your material here. And so over here we have about, this is the before deposition, and this is the after deposition, about 5 nanometer coating on our TiO2 nanotubes. And here this is about 40 nanometer coating, and the big broad background is from the glass substrate we used. As you can see, it took a lot to actually get an XRD sample on this. And unfortunately, I don't have time for this clicker question, but so if you have 10 seconds, why does the growth rate increase with more indium macac doses?
Start.
Oh, I'll start. Sorry, I'll start the clock over. 10 seconds. Go. Films are deposited with excess indium. So basically, what we're showing here is the growth rate increases. So you can multiply the number of indium doses 1 second, 30 seconds off. And if you do this a few times before you do your sulfide precursor, you get more growth. And so that's shown here with the growth per cycle. And so the other option is that you have indium macac on the surface, more fully terminated. And this last is adding extra indium macac. We use residual macac. Macac is acetyl acetylnitrile, acetyl acetone, which is a great ligand in metallic chemistry. And so here's a third one here. So I don't have responses in. All right, most of you think C, and well, you're wrong. Sorry. It is actually B. Sorry, I'm wrong. It is actually A. It's B. More indium macac terminates the surface. So basically, you put on a little bit of your indium macac, but it doesn't completely cover the surface. You have to purge out the gas. Then you put more of your indium macac, and a little bit more sticks on the surface. And so what that brings up is actually quite poor reactivity of your indium precursor with the surface. And so in atomic layer deposition, you want to do a lot of things to improve the reactivity, and I have a few slides on that. You can see them online, but I'll point you to this review by Roy Gordon at Harvard. There are limited precursors for atomic layer deposition, and chemists can really help by developing some of these, and chemists have done that in the recent past. So if you have aspirations to help out in ALD or other fields that I've shown today, hopefully some of this has helped you. Thanks.
Right. Is there any very burning questions that we can ask them right now?
There was a slide where there is some mixture between tantalum and Pixie to produce some oxide. So why do they do this mixture? Why not just using tantalum or Pixie?
I don't know that question off the top of my head. It probably has something to do with how the orbitals mix on the two and give particular structure. It could also have to do with the doping. So making a level that is effectively a level within the band gap of that metal oxide. it's accessible.
Any more questions? No, let's take 10 minutes and then we'll have